at least from our course and from our university. Hopefully we get to see him more here as a student. All right, so last time we looked at this eccentric loading case, basically axial load with an offset, and we said it induces both normal stress due to axial force F over A and due to bending MC over I, and you guys helped me with calculating these. My feedback to you guys is some of you were very quick in calculation, so great. As an engineer, you're supposed to be calculating a lot of big equations, and we've done already so many of those in this class, but you need to be precise too. So some of you stayed after the class and you wanted help, absolutely fine, but I want you to be really good at calculation. So one of the things is this: pay attention to the numbers that you see on the screen or on your notes. The other one is you have to know your calculator well. So one of the things is this: I think these days everybody's calculator is really modern, except mine. Even mine allows for storage capability. Basically, you can store this big number. You calculate it once, you store it as A. If you want to know how, come to me after class, I'll show you that. And then you calculate this as another number, store it as B. So this number is A, this number is B, so you don't have to recalculate these. So take advantage of that. You want to really know your calculator well. Take advantage of that. Practice with me in class. You resolve any issues that might arise, and then the test, even one time should really suffice. All right, so that's my feedback to you on that. One thing is left is this position of the neutral axis that we want to calculate. So on that, so we already calculated this stress and this, so let's put these on the cross section. We said that this is basically viewed in this direction, and this is point C. We call this stress profile. So on top, we found that to be 2.5, and that was compressive. That's why I put it inward, 2.5 gigapascal. And on the bottom, we calculated that to be positive. That's why I pointed outward, but slightly bigger in magnitude, 2.71. That's per our calculation. So on this side, put this for your test. If force is axial, that means no offset. If it's axial, we know that there is no bending, but I wanted to talk about pure bending. If pure bending, it could arise with M alone, the moment alone, then we know that neutral axis, NA, neutral axis, occurs at the centroid of the cross section. We learned that already. If bending is not pure, what does that mean? Like eccentric loading that we're talking about here. Eccentric axial force. Again, force with an offset. The force is in here, but there's an offset to the cross section of interest at C. Then neutral axis gets offsetted from centroid. So keep these in mind. So that means actually it shows up in here too. So this, if I connect these two, if these two were equal, if we did not have offset, these would pass through C. But because these two are not equal and opposite, these do not pass through the centroid. There's a little bit of offset there. We want to calculate that. So this overall is 1.2 centimeters. I want to calculate this length. So let me choose a different color. So let's call this H. And we know that this is 1.2 centimeters minus h. So if I write this in centimeters, this is also in centimeters. Stay with one. If I want to convert it to SI, convert both to meters. So all of these units are in centimeters now. How do I calculate this? Well, this is not a solid problem anymore. This is a simple geometric problem. Look at the top triangle. Okay, you brought your backpack already, right?
Yeah.
So I do not want to put weight for you then. You were here. All right. So this is the upper triangle. Look at the bottom triangle. These are similar, which means you can scale them. So it's scaled similarly. So you can scale them to get to the same dimensions. That means the scale, whatever that is, that means the ratio of the size has to be the same. So similar or constant. So constant side ratios. So that means if you look at this length, that's 1.2 minus h. If I look at the bottom one, it's h. And if you look at the horizontal one, it's 2.5 giga. The lower one is 2.71 giga. Giga cancels out. So look at the corresponding sides on the two triangles, divide them, and these all should have the same ratio. So this is all really a constant value. I do not need to put this for the hypotenuse. All right, this has one unknown in it, one equation. We know that cross multiplication gives us the only unknown. I want to finish up quickly because there's really not much other than math. So solve for h, again, the result will be in centimeters. 0.62 centimeters. So that means this little offset is 0.02 centimeters. It got offset by 0.02 upward. Yeah, we do not do much with this kind of calculation, but the textbook really covered it with a lot of examples. But there's not much more to this. So that's why I'm giving you one example. That would be really the extent of it. So with this, we completed the last example. I'll give you time to complete your write-up. And any questions, guys, for me? I'll give you time. Yes.
What does that say next to the triangles and red at the top?
Similar, they scale similarly. And then constant side ratios. Just say, if you ever hear that people are giving a award for worst handwriting, nominate me. So in engineering, it's really this. We draw equations from different topics to get the problem solved. In this course, we're mostly talking about mechanics of materials. So equations come, or properties come from materials, from mechanics, and then we take advantage of geometry as we just noticed, and then we do a lot of mathematical derivation and calculation. And in other courses in engineering, you do a combination of this and other things. So that's why you take a lot of mathematical courses early on. You should really be equipped for those courses. All right, I see that you're done with your calculation. As before, you have your calculators up. You're ready for calculations. So you want to do this example. And as before, while you're writing down, think about application. Where would you see applicability for this kind of problem? I'm not talking about the statement, I'm talking about the geometry, that load that you see with an offset from the center. Go for it, believe in yourself.
Could it be like a skyscraper, how they,
Make it statement.
and a
It is.
skyscraper being,
Okay.
when the skyscraper kind of tilts, that could be,
But the load is sideways, right?
yeah,
So that's not the case then,
no?
unless you lift it upward.
Oh, that could be,
Yeah. So work on that, yes.
Could be a trussed bridge, like the road on a trussed bridge being pushed towards.
If the cross section is not rectangular, if it's not symmetric, yes. Tyler, point, wait and come up with something. Go for smaller or bigger dimensions. Yes, Nathan.
I don't really know the name of it, but in like a trailer, there's the
Hitch.
shaft that goes to the hitch, that load.
I was waiting for that. We're mechanical engineers. Yes. Twin hitch. Crane that has that hook the same way. You hang our clothes. When there is non-symmetry, that happens. So all those cases, this problem applies. So really the same thing, only dimensions, cross-section, shape changes. So the force is deployed at point D with some offset from C. Dimensions are given, and the goal is to solve for stresses at different points, A and B. Why A and B? Because these are the extreme points. Perhaps those are the most critical ones. So we calculate stresses at those 2 points, and then compare with material properties if given, and we make that decision, whether it's a safe system or not. So this is from textbook, and with some simplification. Again, just to get the mathematical burden away, but really have mainly our engineering discussions. So as before, we follow this approach. First, pick a coordinate system.
Can you zoom in on the diagram?
Nathan, are you? Okay. Nathan, is that you or?
Yeah.
Okay. Yeah, if you want to take a picture now, please do so that I can zoom back and write on it. All right, pick a coordinate system, stay with it, whatever that is. Pick one, stay with that. So put it, again, at at centroid of interest. This is important, guys. Guys, I will talk about the terminology later. It may help you. At centroid of interest, what does that mean? Eventually, we're interested in stresses at these 2 points, A and B. So look at A and B. They share the same cross section. So draw just the cross section at that point. The centroid of interest is the center of that point, really here. This is the centroid of interest. If you follow that, that would be really easy for us. Just follow instruction. All right, we pick a coordinate system. So 3 mutually perpendicular axes. Pick any names, but right-handed system, which means if you put your 4 fingers of the right hand along X and rotate them toward Y, the thumb of your right hand should point to Z. That's a right-handed system. In engineering, 99% we want that to be right-handed system. All right, whatever we picked, whatever labels you put there, stay with that. We picked the coordinate system, and then we say develop stress equation, basically in parentheses, in a modular form, right? Enumerate axial / bending effects in a modular form. For axial, we know what the stress equation is. If there's bending, we know what the stress equation is, so we superpose them. So what we do, we already picked the coordinate system. Let's develop our stress equation. So stress, normal stress, sigma. So let's do one at a time. Axial. We're pulling on the system, therefore there's pulling on the entire cross section. For pulling, we know that it's F over area. So P over area. Because we're pulling, it's positive. If we were pushing, it's negative. So plus P over A for the entire, any point on the cross section. All right, plus P over A. Axial, we're done. At most one of them. Now let's talk about bending. Now this part, again, visualization. Engineers, again, think about that. Engineers, you have to be good at visualization. You opted for that. So you should be really good at visualization. So look at force P. When we say bending, ask yourself this question. Does the system buckle about any of the axes? Does it buckle about any of the axes? Open question, guys. Which axis does it buckle about? Yes?
X-axis?
About x-axis. X, you see that it's on the center, it's in line with D, with P. Does it buckle about X? Buckle is like this.
Oh, so I think it's Y.
Which one?
I think you just said it, but it would be the y-axis.
Any other opinion? Then there's one more left.
The Z.
The Z. Right?
It's one of them.
One of them. But it's fair, right? You said that, you then guess the point. So buckle is about bending, right? It curves around Z. I'm sorry?
You answered it for me. I was just gonna say we buckle around Z because it's rotating along that axis, correct?
Yes. So you said it then. Or no. Just you tell me. Do you deserve it or not?
I guess so. I said the right answer, so I guess so.
All right, I'll give you a point. If you did not say, it would have been better and would still give you that point. All right, Ethan. Yes, when you say buckle, Jacob, just it's about curling about that axis. So it curls around Z. So it curls around Z, it doesn't curl around X, it doesn't curl around Y, no bending about those two axes. So it bends about Z, then MC over I about Z should be there. So we know that it could be plus or minus depending on the point. So MC over I, but M and I get the same subscript, which is Z. So we develop our equation. All right, now we're interested in A and B, so rewrite it once for A and put CA for that. And then that's why I put this reference, CA sigma A. Repeat it for B. Now we want to pick signs. Volunteer, please raise your hand, I'll help you with that. Drew, are you raise your hand? Or you're not sure? All right, anybody else? Yes? All right.
For A, the MZC, the A over I, Z would be positive in this situation.
For A, you said is it positive or negative?
Positive.
Positive, and it is positive. So we said we're bending about Z downward. So the top face gets elongated. For that reason, top face should be positive. So pick positive for that. The bottom face, it gets wrinkled. So it gets shortened based on our terminology. So shortening, compression mean the same thing. Pick negative for the bottom one. All right. Now the equations are set. You see that MZ and IZ are recurring these equations. So that's why I left this space here for these. Calculate them once and reuse them. So volunteer for MZ, volunteer for IZ. This is really a repeated topic. Volunteer for MZ, volunteer for IZ.
For IZ,
IZ, okay, go for it.
1 over 12 times base times height is 1 of them cubed.
Thank you so much for saying it like that. And the next example, you prove that this way of saying that is the best. So base and height, and one of them is cubed. You said that one that is?
One that is cubed.
Yes, which one is cubed? Justin.
Base.
No, give me the formula. Which one is cubed?
Oh, which one's cubed? 112 base cubed times height.
No. You said 112 base times height, one of them cubed. Which one is cubed?
Oh yeah, which one's cubed? Base.
How will you say it? How will we determine that? The one that is? All right, Hero.
Perfect.
At the same time, you go for that too.
Particular Z-axis.
We're going to do that 2Z in this case, right? Just like which one is that?
Particular Z is
Look at the two cross-sectional values, 40 and 100. Which one is perpendicular?
B equals 40 millimeters.
Which one is perpendicular to Z?
Oh, the D, the height.
The height. Just I did give you a point, but be mindful of that. 1/12 of base times height. The one that is perpendicular to the bending axis gets cubed. All right, so we said it's 40 times 100, and 100 we determined to be cubed. Immediately we know that's 10 to negative 3, and this is 3.33 times 10 to negative 6 meter to the fourth. Remember, I is a measure of resistance to bending. All right, another one here for MZ, guys. Awesome.
60 multiplied by 10 to the third.
That's the force. And then times? Yes, distance, which is?
I don't know.
Anybody else? Ivan?
5 millimeters.
25 millimeters. Perpendicular distance between the force and bending axis. So it is really this distance. This little. You see that here? This little. So this is P times DC, the distance DC, absolute value of that. All right, Evan Muchler. All right, so we have everything set. Now let's just plug in values. So P, actually, I volunteer for CA value. View this as a test, test yourself. CA, what is that? Jacob,
Would that be 50?
make a statement.
It
It is 50. So remember, we said if the bending axis is found, put these arrows, measure in those directions. So go from here to the point of interest. Go from here to A, you have to go 50 up, that is 50. So C is 50 millimeters, and so is CB. Guys, again, it's about instruction. The person who developed these gave us these instructions. If you follow that, then that's great. You will get it correctly. Jacob knows them all. Now we have everything. Let's plug in values. 60 kilo, 1023. Area is base times height. And we don't have to look them up again. It's these values. And MZ, let me put that in here, 60 times 10 to the 3. And then D is 25 millimeters. So this is 1500. All right, area 4D times 10 to negative 3, 100 times 10 to negative 3. MZ 1500, CA 50 millimeters, and IZ we found it to be 3.33 times 10 to negative 6. All right, guys, your time. Your time. If you have Jeremy, our guest here, but I have to say it to you because it seems it's important. I found some of you not being honest. Unfortunately, you read the test, I saw some issues, some of you were looking at other people's work, and that's not appropriate, and some of you, when I ask you to do that work, and show that to me in class so that I give you the point, some of you bring in somebody else's work. That's not appropriate, guys. This is, I happen to know a little bit about solids. I'm doing this for you guys. So earn that point for yourself. Please, be honest. So let me give you the value, and then you make sure you found these values and then confirm it so that I give you a point for that. This way, you don't have to come here. This is negative 7.52 megapascal. Again, to convert it to mega, we know that you have to divide by mega, which is 10 to 6. Confirming both, right? Aussie, yes?
I got 35.52. Just subtracting.
Yeah, here, I want to make sure,
Yeah.
as only you got it, whether you calculate it or your mind doesn't matter. All right, point to you. Okay, radian. Again, if you're not familiar with storage capability of your calculator, come to me after class, I'll help you with that on your calculator. You got that? Both? I'm not going to put it forever on the screen, so make sure you do that before I switch. you don't have to bring it, just raise your hand, I'll give you, unless you have a question.
I can't read your hand, okay.
Which number? 15, yes, it's here.
Yeah.
This correspondence.
That's the same.
So, let's see that.
Evan Josiah. I gave you the point, yes. No worries. Spider. All right, so you said we do all this calculation for a reason. And the reason is this system safe? Then we have to know the material property. Textbook did not give anything. So suppose strength in tension is given as 40 megapascal. And suppose sigma u in compression. I mean, these are just arbitrary numbers just for us to be able to comment on that. 5 megapascal. All right, 2 volunteers. 1. All right, next to each other. Justin, based on this alone, strength tension, is the system safe and why?
Based on the tension, yes, because the number is less than the ultimate.
Strength.
Ultimate
Yes.
strength.
So this is greater than 30. This. So A is safe. All right, Jacob.
B is not safe because it's higher than 5.
Great. So as easy as that. So this is less than 7.52, so B not safe. Jacob, overall,
Not good.
not safe. 1 failure, too many. Guys, remember, 1 failure, too many in engineering. So that means if you still want to use that hitch, for instance, Nathan gave us that example, then you have to work on the bottom point, because point B is not safe. You have to strengthen that point B, or minimize this distance, so that it creates less moment, therefore eventually it creates less stress.
Yeah,
So it's a
that's-
design
you should
thing.
get that. You should get this one.
All right, guys, any question on this?
I think you have to add the other one.
Yeah, I did.
You did.
Yeah, that's what's up. When I add it, I get this number.
Nick, Dylan, I see you guys are discussing. Can I help, or are you?
Yeah, discussing the negative on the answer for 7.52.
This number?
We're looking at absolute value, right?
Okay. It's just
When we say
magnitude.
compression, we're just looking at compression.
Okay.
Negative
I got
sign
E to this.
just signifies that that is in compression.
Is there anything to do with the direction?
Is it?
It's just compression.
Compression means negative, right?
Okay.
Yeah, I've been doing it by section, like what you showed me.
Yeah, yeah, I'm just saying.
Tension
You
is
go to
positive.
mode,
Mm-hmm.
and you go to.
Science.
All right.
Mm.
If no more questions, let's move on to this one. And you may have already looked at homework, and you have a similar thing there. Guys, if you do not pay attention to this, solving this on homework is not easy. And the textbook is in love with mathematical complications like this, because now we have to deal with 2 axes for bending. And a lot of nuances there. We have to be really attentive to details. But we crack it together, and again, it's about following our instruction.
No, the first one was this.
First two, you good? 1.5. E, sorry.
like the first part. The P over A. Okay, yeah, technically, yeah.
Bring it in, Jesus, what's the issue? About table 12, please.
I think I messed up my calculations. I'm trying to figure out where I messed up. I get 15
While
megapascals.
other people are working on it, I'm going to look at yours.
Okay.
Brady, you got it?
Yeah, I got
But
it.
you didn't tell me so they give you the point?
Pardon?
You didn't tell me so they I give you the point?
Oh, I forgot. That's
Oh, okay, that's just a number, I can't work like that.
Oh, sorry. I
Me.
was doing this. I did by separate parts. So I did this,
Mhm.
and then
you divide it by,
I divided.
oh, you multiply
I
these
multiplied,
first,
then
I
divided.
saw that.
Mhm.
And then you divided this by that, and you got that value, that is good.
Yeah.
So you know that you could do it like this. Can I
Yeah,
give you
go
an
ahead.
option? All right, but how do you reset that first? Clear? All right, clear?
Yeah. Okay.
Like
yeah.
that?
Yeah, you clear everything.
Or was it easier?
It's
too late now.
Yeah.
All right, too late now. All right, so that one. So I would do like this. Let's do one at a time. This one, right? So I do, because this denominator is bigger than the numerator, I do the denominator first.
Okay.
So 40, how would you do time 10 to raise is,
Second 10 to the negative third.
oh, okay, let me erase it then.
Okay.
Because 40, you do your thing.
Yeah. Second.
Actually, you do that.
Okay.
40 times 10 to negative 3, you do not do anything else, just follow that.
To negative 3.
All right, multiply this thing by 100 times 10 to negative 3. All right, hit enter. Then invert this so that you bring it to the numerator. Invert it. Raise it to the power of negative 1.
Okay. Is it?
Raise it to the power of negative 1. Is it this? Okay, negative 1. Enter. Now it's in the numerator. Multiply by 60 times 10 to 3.
60.
10 to 3. Or enter. You have this, right? Now you want to store it. Just watch here. We did all this calculation, right? Store. Just hit this, and then pick your variable. A, B, C, you see green letters? Pick, for instance, A. Hit enter. From this point on, A
This. Yeah.
is that value. Now start over for B. Work on this one. Say, call that B, and then do A minus B. It gives you the answer.
Okay.
Do A plus B for that, A minus B for that.
Okay.
Okay? You said you did it, you confirmed that?
Yeah.
I'll give you, no, I trust. I didn't give you the point before.
No, I don't think so.
All right, so the first instruction was pick the coordinate system at the centroid of interest and look at A and C. This is from the textbook, and the coordinate system is already put for us at that point. The figure is not great, but let me give you this length, and this length are basically this in the middle. So really this is 40 millimeters, so is this one. So this side is 60, right in the middle, and so is this one. Again, visualize this point being at the center of the cross section. So the coordinate system is already worked out for us, so work with that. You don't have to do any changes. Again, so we did this one. Coordinate system is already there. Now develop stress equation. So sigma, leave some space for certain calculations. Maybe I do it here.
Times 50 to the 10 to the negative 3, right?
Now, Jesus, I suggest now you pay attention to this one so that you not miss this. There's always time for that. In
Okay.
the break, you can do that.
Okay.
All right. So we said enumerate the load effects in terms of axial and bending. So axial. Whenever you see a load like this, pushing or pulling, yes, there is F over A. You're pushing, it is negative. So negative F over area is there. Negative because you're pushing again. All right. Now, let's talk about bending. Now, So when you say bending, ask yourself this question: does it buckle about any of the axes? Yes. First, visualize this. It buckles about X like this. Therefore, put MC over I about that axis. So plus minus MC over I about that axis. Parentheses, subscript X. And it turns out there is bending about Z also.